And here we are once again. It is the physics video lecture, psci 168, video lecture 15. And we're at a really important point in the semester. This is central to everything we're doing. We've been talking about work, energy, power, conservation of energy, and hydropower. So I'm going to review those things and then review the hydropower discussion that we had last time and take it a little beyond what we had done. But very important that we review these things. So our main topic is hydropower, but it's worth reviewing work and energy, work, energy, and power, and in particular what's called conservation of energy. Conservation of energy. And yeah, so first of all, work, energy, and power. We had force times displacement, a force times a displacement, and the real basic example that we've used again and again is that the work is equal to a weight, which we now know to talk about mass times acceleration due to gravity, times a vertical displacement h. So we use this again and again. So this is central, and we had many examples of how this work, which we could also call potential energy, or potential energy, we had many examples how this formula would come into play. Potential energy. For example, the grandfather clock. Okay. And with the grandfather clock, we lifted the weight by maybe turning a key or something. We lifted that weight, we cranked the weight up to a certain height, and this was the stored energy, and then it ran down in the course of a week, and so we would have power equals mgh divided by t, and we just took however much weight we had, whatever height we lifted it to, and whatever the time was. Now that had to be in seconds. This had to be in newtons times meters, seconds, and then we would actually have watts. So important is also our units are kilograms, meters, and seconds. I'll even write that out in words. And kilograms, meters, seconds. So we either use those units or convert to them, and then it's very useful because all of our expressions are consistent and they pretty much take care of themselves because we're not doing anything too complicated. And of course, this m for meters is not the same as this m for kilograms. You just have to know things in context. Good, so that was work, energy, and power. Now what about conservation of energy? In order to talk about conservation of energy, we had to introduce the idea of kinetic energy. So in addition to the potential energy which we're using, the gravitational potential energy is just mgy. There's our y-axis, it's up. We also have, okay, so potential energy, we can put a little g there for gravity if you want, okay? And y is just the position along the y-axis. Then we also had kinetic energy. And we got that fair and square once we had Newton's law and the mass and everything. And the kinetic energy is 1/2 mv squared. So in order to understand energy conservation, we had to see how potential energy could be converted to kinetic energy and back again. And the example we use is the pendulum. So the pendulum example, where we suspend a pendulum somewhere, and actually in this room under other circumstances we'd have a big bowling ball pendulum, which makes for a great demonstration. But yeah, this can swing along this semicircular arc from various places, and I'm just going to really draw our attention to this fact again. If I release the pendulum from rest at this point A, it will never get higher than the point B that's on the same level. In reality, because of friction, it will actually not quite make it to B, and then on the way back it won't make it to A again. And after so many oscillations, it'll actually end up back at the bottom. Okay? If you were to see a film, a movie of a pendulum starting out small and growing in its oscillations, you'd know that that film was being played backwards. Okay? So the pendulum example shows what we're calling conservation of energy. It shows that we can have potential energy converted to, you know what, I'm going to use a little more room here. It's showing that we can have potential energy converted to kinetic energy plus some potential energy, converted to all kinetic energy, and back again, etc. So conversion of one form of energy into another, conversion of potential energy into kinetic energy, is what the pendulum shows us. And the impossibility of releasing it from rest here and having it swing higher, that's the example of conservation of energy we really have to be clear on. So conservation of energy, I already stated the definition that I want you guys to know. Conservation of energy, and I'll repeat it, the energy is neither created nor destroyed. It's changing form. Energy cannot be created, that's a C, nor destroyed. It changes form. So let's take the pendulum again. It's swinging back and forth, and after a half an hour it's down here at the bottom. What happened to the energy? It wasn't actually destroyed, it was transferred to the air molecules in the room. In the ideal frictionless case, this pendulum would swing forever. That's the ideal case. Now, in terms of energy being created, that would be the case if we released it at A and it would swing all the way up to B plus something. Because that extra work, where would it have come from? That's the point that's made here. Now this had to be learned, and it hasn't been learned by everyone to this very day. Okay, I'm not asking anyone to believe it, but rather to understand it. But there are still people who are trying to make mechanical contrivances that will somehow violate this thing. But you always want to remember what you're trying to do is to get this impossible thing to happen. The reason we have to know this is because we have a civilization to run that needs enormous amounts of energy. And there are ways of obtaining that energy, but trying to get it for free somehow, violating a natural process, that's just a dead end. Okay, so for that reason, we're going to be talking about large-scale energy production, and this lesson had to be learned in order, for us to systematically go about obtaining enough energy to run our entire operations. So this conservation of energy topic is important for that reason. Now, the next thing I showed you was those slides of the attempted Perpetuum mobile. Yeah, that's the terminology I didn't bring in last time. So let's bring that into play here. So, a machine that violates conservation of energy is referred to as a perpetuum mobile. Now there are two kinds. Perpetuum mobile of the first kind is a machine that runs, perpetually, from which you can also extract work. And that, that ancient sketch that I've showed you guys, and that if it doesn't print out well, I'll send you a file. But that example with the tank of water up above, which sends water out to turn a water wheel, and then there's a knife grinder sitting over here, sharpening a knife on a grinding wheel. Okay, so that knife, I'll call it the knife grinder example. That's an example of a perpetuum mobile of the first kind. It's supposed to run uninterrupted, and the water was lifted back up into the tank. It's supposed to run uninterrupted, and you're even able to get it to do useful work for you. Okay, that's a violation of the theory of conservation of energy. The second kind we can't talk about yet until we learn about thermal physics, but we'll get there as well when we get to thermal physics. So those ideas have been tried. It's a great idea. Imagine you could lock that little water wheel thing in a room and just have it circulate and do work forever. But now we're on the hydropower topic, and this was an attempted hydropower, a theoretical attempt, but the real attempt was already shown in the first slide, where they have a very gigantic water wheel, and there you're bringing water in from a great distance. You're not locking it into place. So good, we have this perpetuum mobile, first kind, and both of these, let me put that as a note before we go on. They violate conservation of energy. Actually, let me correct that. The first kind violates conservation of energy. The second one we're not ready to talk about yet. Okay, so once we've gotten away from that kind of wishful thinking, now we can actually inspect the world and see how energy is obtained. And that brings us to, I kind of want to segue off of these images that I showed you, brings us to the hydropower topic. And there I'm just going to repeat that sketch and add some information to it, and maybe get a little assignment out of it for you. Typically with a class, I like to show a bunch of information slides and even some Google Maps, Google Earth type of information, because we have a lot of hydropower projects up in our mountains here. So I think I'll assign that to you guys. I'll tell you what to look for, and we'll see how we can do there. Let's count some minutes here. Okay, good. So now we're back to hydropower. And this sketch that I like to do, but we're going to extend the sketch now. We'll use it more than once this semester. So now we've got a lake behind a dam. So there's a mass of water held back by a dam. The dam usually blocks off a valley or a canyon. You store a lot of water there. Now the reason that water is potential energy is because it is above the powerhouse. So this pipe here that goes down to the powerhouse where the power is generated is called the penstock. And we'll just call this the powerhouse. And the kind of operation we're thinking of is going to have a water level up here. I'll make this blue. And the powerhouse will be below the water level of a lower body of water. The lower one doesn't have to be as great as the upper one, but we have the lower water level and the upper water level. And the height difference between these two water levels, regardless of where the powerhouse is, it's that height difference that measures the potential energy. Okay. Because if you take a cubic meter of water from down here and bring it up there, that would take a certain amount of work. And if that cubic meter of water comes back down to this lower level, that's how much work could be obtained. So I'm using work and potential energy interchangeably. So over here on the right we have mgh. However you want to measure the quantum of water, you could say it's just a little layer of water on the top corresponding to a little layer on the bottom, or it could be a more substantial part of it. So that's the potential energy. Okay. So the first point is that not just any body of water represents potential energy. Okay. It has to be elevated above a body of water. If you just had a lake here in the valley, a big lake, it would represent zero potential energy. It's just a lake at the base of the valley. It has to be elevated. Okay. And of course that letter H tells us how much. So if this were in the base of a valley somewhere, H would be zero, no potential energy. So potential energy, because the water is elevated, okay, so love to number things. So then we have water flowing through here. Okay, and there's the machines in there, and then it flows out through there. So potential energy, as it's running through, it's kinetic energy, it's spinning the turbine, doing all that. When it emerges again, it's completely at rest. But where has that work gone? It has turned the turbines against the resistance, and when we get to electricity and magnetism, we'll see how that can actually be turned into electrical power. But for a given amount of water up here, you can get the given amount of energy done as work, as useful work. Okay, another point, just in practical terms, some dams have their powerhouse right at the bottom. So that would be an example on the Colorado River Hoover Dam. Okay, so let's just put some dams have the powerhouse right at the bottom. base. Okay. Then this H just measures the height of the dam. You'll notice I didn't draw it that way because up in our mountains, for instance, we can have a dam at some very high elevation lake and run these long penstocks down the side of the mountain and put the powerhouse much lower than the height of the dam itself. And again, the greater the height, the more energy involved. So that's why that's done. But yeah, in terms of what the example I was going to give, we would have dams like Friant here in town, Pine Creek, Pine Flat Reservoir, and then over in Nevada, Hoover Dam. So others run the pipe down the side of the mountain. A lot of our dams coming out of our power plants being fed by, say, Shaver Lake, Portright, etc., run these long steel penstocks down the side of the mountain. Okay. So I could even say Hoover Dam, I think it's 700 feet, so let's say approximately 200 meters high. These are much smaller than your other dams. I'll just use Portright, and Washon, and many others run much longer penstocks. Run penstocks with H more on the order of 500 meters, and even more, 600 meters. Okay, so that's part of the hydropower discussion. Actually, I want to keep improving on this picture here. Yeah, this time, how did the water get from here to here? Where did the work come from to raise the water from lower to an upper reservoir? So fundamentally, we have to talk about the water cycle. I'll keep this right here. And the water cycle, of course, is driven by the sun, so we find that our hydroelectric energy is actually a form of solar energy. So we can say the water is lifted to the upper reservoir fundamentally by the sun. Lifted. By the sun, right? So we have evaporation and the water cycle. So understand how that plays a role. We're actually have to study solar energy. Right now that's just in the background, and we could put that in our cartoon as well. And then we're going to talk about the power formula now. And that is just out of our potential energy expression. So power is mgh over T. We had that for the stair climb. We had that for the grandfather clock. But here, we're just going to put parentheses around M and T. Same formula, but now we see there's a flow rate. Okay. And so the power can be controlled. G and H are fixed, but the flow rate can be controlled. The example I gave last time 1,000,000 watts, and you can make up other examples. But a large-scale hydroelectric project will have 1,000 million watts, 1,000 megawatts. Example last time was 10 to the 6 watts. large power plants 10 to the 9 watts. Okay. Okay, so we'll come back to that. Okay, so we've got that power formula. Now I want to talk about energy conservation in this regard. If we use this definition, a certain weight of water at a certain elevation, that's how much potential energy is there. That is the maximum energy that we could conceivably recover from that by running it down here. In reality, there are going to be losses. You could say frictional losses, heat losses when you're generating the electricity. There'll be many losses, but this is a principal formula because this is the absolute maximum. To have this water up here with respect to that reservoir and to think you could get more than MGH, that would be the violation of energy conservation, which will never happen. So for that reason, these formulas are, are set in stone, so to speak. You can trust these. It's an upper bound, we say, on the total amount of energy that's available. Okay, so now let me formulate a problem for you guys. Because we want to be able to work with this. I did that example last time. I think I'll repeat it. So we want to be able to calculate energy amounts for personal, city, or the entire civilization, and we can do it in terms of just these formulas I've given. So that I want to do systematically now, and I have to give a couple of definitions first. So let's see. We'll leave the picture up there. I'll erase this and bring in the definitions. The problem is this: you've got a lake, you've got a certain height, you've got mountains, a lake, canyons, etc. How much water represents the energy needs? Okay, everybody who pays their energy bill can read on it what type of energy it is. So that's what I want to put in here next. So energy units. Okay, we're not doing thermal physics yet, that comes later, so we're just doing the mechanical energy units, but we'll see they're also used in electricity, in your electricity bill. So first of all, we have the joule, which is the Newton times the meter, right? It's the joule. And that's the energy unit, and we have a real feel for that. For example, if I climb the stairs 5 meters, I've done 4,000 joules of work. Okay? So we definitely can have an actual feel for what that energy unit represents. Now, the power formula gives us another one. When you pay your energy bill, you're actually paying for a kilowatt hour, and that's maybe a 25 cents, 30. Check your energy bill sometime. So kilowatt hour, that is an energy unit, kilowatt hour. But how does it relate to joules? To figure that out, I'll put question mark. We use the power formula. It's power P equals W over T, and solve for work. Work in energy is equal to power times time. Okay. So we're using units such that we have the joule here equals the watt, which I'm going to write out, times the second. Okay. So what is a kilowatt hour? A kilowatt hour is 1,000 watts times 1 hour, which is 3,600 seconds. So 1 kilowatt hour equals 10 to the third watts times 3,600 seconds. So let's put that in scientific notation. 3.6 times 10 to the 3, 4, 5, 6. So it is 3.6 times 10 to the 6 watts times seconds is joules. Joules. In fact, 1 kilowatt hour, 3.6 times 10 to the 6 joules. 3.6 million joules. Okay, so now we can figure, see, you don't even have to memorize this, you can just look it up. This is a conversion from joules to kilowatt hours. When we're calculating M times G times H, that's joules. We can just convert it to kilowatt hours. So I'll do an example and then I'll give you guys some more to calculate. And that power formula we'll use again. So just a simple definition, we get quite a bit out of this. So let me give an example. I'm thinking of Courtright Reservoir. So suppose we have example 10 cubic meters of water are elevated a height h equals 500 meters. This is a good example. 10 cubic meters of water, that's a few of these desks. Well, you're not seeing the base of the desk. Cubic meter here, and then 10 of these. How many kilowatt hours does that represent? How many kilowatt hours of potential energy? Question mark. Okay. And this is a good example because it's a big chunk of water, a small pool's worth. On the other hand, this 500 meters is the height difference between Courtright and Wishon Reservoir, so we have that right up here in our mountains. And in fact, power is generated for us in those power hydroelectric plants. So 10 meters cubed of water. So here's what we have to do. The potential energy, remember I'm using energy and work interchangeably, you just got to get used to that. Potential energy is mgh. Now that is 10 to the third cubic meters, no, 10 cubic meters, sorry, times 10 to the third kilograms per cubic meter. That's something we have to put in our list of important facts. A liter of water has a kilogram mass, a cubic meter of water has 1,000 kilograms of mass. I'll put that in formally in a bit. G, we're going to use 10 meters per second squared. So that's M and G. This right here is the M. Right? The meters cubed cancel. So that gives us kilograms, meters per second squared. Those are the newtons. And then we have 500 meters. And we have 5 times 10 to the second, third, 4, 5, 6, 7. So we have 5 times 10 to the 7 joules. 5 times 10 to the 7 joules. So how many kilowatt hours is that? Well, we can just do the conversions right there, so I'm going to leave that up. We can do that conversion. Just rewrite this number 5 times 10 to the 7 joules times 1 kilowatt hour divided by 3.6 times 10 to the 6 joules. And we have 5 divided by 3.6. I'm going to leave that there because that's just some number between 1 and 2. And we're just left with 1 power times 10 kilowatt hours. So if you can do this, you can do anything. 10 kilowatt hours, that's about, it's about 13, 14 kilowatt hours now, or 15. That's not going to get you that far, so you're going to need more of that up there. But that's how a conversion like that is done. And 3, 4, 5, 6, 7, a 5 in front. Yeah. So suppose instead of a small pool worth of water, you had a very enormous lake. And you could calculate larger amounts and you just use your powers of 10. And you could actually figure out how many kilowatt hours you use in a year in your own household by just reading your electric bill. And you could figure out how many cubic meters of water Courtright Reservoir would have to have in order to generate that power there. So let's wrap it up with a homework problem. And we're going to spend a little more time on hydropower without a doubt, but this is a good practical application. I'm going to collect some of these things here in a little chart. So we need some facts here in order to do these kind of calculations. So first of all, I'm going to use potential energy, mgh, power, m over t, gh. And if you want to use g equals 10 meters per second squared like I just did, that's fine. Or you can use 9.8, whichever you prefer. Now, we have m equals rho times v. Remember we had those Greek letters we printed out? That's the Greek letter rho, and it refers to density. So mass is equal to density times volume. Okay. And the density of water I'll just use the letter rho again, is 1,000 kilograms per cubic meter. So that's something we have to be aware of. And we can just use it the way I did in my formula right there. G is, of course, 9.8 meters per second squared, but you can use 10 if you want. And H is the height in meters. So yeah, these things we have to get used to. M over T, of course, is the flow rate. M over T is the flow rate in kilograms per second. So it's mass over time in kilograms per second. Okay. And we also had, for the conversion, we have 1 Newton meter is a joule. 1 kilowatt hour is 3.6 times 10 to the 6 joules. through those conversions. And finally, for the power formula, we have, I'm just going to write this. We have power equals work over time. Okay. Energy over time, work over time. So we can use this in a few different ways. First of all, in that way, example in that power formula right there. We can also have work is equal to power times time, which we did for the definition of the kilowatt hour. So that's the second equivalent form of this, just by cross multiplying. We can also write time is work divided by power, or energy divided by power. That would be interesting if you wanted to know how long will it take for this reservoir to run out. If that were your concern, you could use this formula right here. And all three of these just come from this original definition. So we'll put these in words as well. So power equals energy divided by time. And that's the first one. And here we have energy equals power times time. And over here we have time in seconds, right? Is energy divided by power. So again, if you have one of them, you have all three of them. So now I was going to give you guys a homework problem. Do I have time? Yes, we do. Okay. So now I'll formulate a homework problem. And that is the following. We'll do it with respect to this example right here. Okay, so homework. A lake or a reservoir has dimensions let's say it's L equals 2,000 meters. The width is, so that's the length, the width is 1,000 meters. The depth is 50 meters. Okay, so this is a reservoir. Find mass of water. So you want to find the mass of the water in the reservoir. So use the density times the volume. Next, if H equals 500 meters, find energy, potential energy in joules and in kilowatt hours. Okay. And the third part of the question, if the flow rate equals 20,000 kilograms per second, find power and time to empty. So then you'd find how much power you get. That's not written that well. Find the power formula, and also find the time for the reservoir to empty. And yeah, if you can do that, you can understand all of the, you can roughly outline all of the hydropower potential. Because if you take a map, you can figure out how much water your valley will hold, and your map will tell you how high the valley is above the canyon, and so forth. Okay, but let's leave it at that. We've got this is a good homework problem. You guys give it a try. We'll talk about it later. It's actually pretty basic, so everything you need to know is on these two boards. And we'll pick up where we left off next time. Still have a fair amount of topics on hydropower. Okay, see you later.